Hello, everybody. Welcome to another edition of Astronomy for Everyone. My name is Dr. Timothy Day, and I'm in for our regular host, Don Glazier, who has the day off. Today, we're going to be talking about a very exciting launch that's coming up in the next couple of months. It's been long awaited. It's called the James Webb Space Telescope, and it's going to be a sort of a colleague and perhaps eventually semi-replacement for the Hubble telescope, but it does things a little bit differently and with a lot more ability. To talk about that, we have a wonderful guest with us today. Her name is Amy Oliver, and she is a fellow of the Royal Astronomical Society, no less. So welcome, Amy, to the show. I'm glad to have you with us to talk about the James Webb, or JWST, if you happen to hear the shorter version of that.
Yeah, thank you so much, Tim. I'm so excited to be here. JWST is really exciting, not just for NASA, but for scientists all over the world who are conducting research.
I can imagine. So you're living actually in Rio Rico, Arizona, right? And you're mentioned you're FRAS, the Fellow of the Royal Astronomical Society. You're also a public information officer for the NRAO, that's National Radio Astronomy Observatory, and the North American ALMA Science Center. So, Amy, you wear a lot of different hats, and a lot of it has to do with outreach on behalf of NASA, being a solar system ambassador, and your work for these other different observatories, a lot of them in the longer infrared frequencies. Is that a good understanding on my part?
Well, so the interesting thing, National Radio Astronomy Observatory and ALMA are both in the radio, so they have even longer wavelengths than the infrared. They're actually at the very, very far right end of the spectrum, and I'll actually talk about that in a little bit and show you what that looks like.
Okay, good. I'm looking forward to that. So tell me, what is the James Webb Space Telescope?
Yeah, Tim, I'm so excited to tell you about that. Give me just 1 second, and we're going to pull up some visuals for you to kind of look at and get a good idea of how this telescope works and what it's going to do. Tim, the James Webb Space Telescope, also, as you've already said, is often referred to as the JWST, or the Webb Space Telescope, or even just Webb Telescope. Got a lot of names over the past 10 years. And it's an orbiting infrared observatory. Well, okay, I just said a lot of words there. What in the world is an orbiting infrared observatory?
Please share with us.
So orbiting, Tim, means that it's up in space and it's going around something. Okay, so the moon, for example, orbits Earth, and Earth orbits the sun. So in the case of the Webb telescope, it will orbit the sun from the Lagrange Point 2, and you can see that here circled on this image that's on the screen right now.
That's a pretty big science term, Lagrange Point 2. What does that mean, and what does it have to do with the James Webb Space Telescope?
Well, I'm so glad you asked, because Lagrange means, or a Lagrange point means, a position in space where objects are sent and tend to stay. And the reason that that happens, the reason that they stay there, is because the gravitational pull of two larger masses, like the Earth and the Sun, equal the centripetal force needed to keep the object with them as they go in their orbit. Okay, so that just basically means centripetal force is just saying it's going to hold it there, right? So L2, as you're seeing here again on the screen, that's actually located 1 million miles away from Earth on the far side away from the sun. So if you're looking here at this image on screen, you see the sun, and then you see Earth, and then you see L2. And this is actually an image from the WMAP mission. And so it's a really kind of interesting look at how these different points look. So there are these different areas around the sun where we can send objects to stay.
What did the WMAP observatory study that we would send that out to L2 a million miles away?
Actually, I'm glad you asked that. That's a really great question. So Lagrange Point 2, I'm going to back up just a little bit and tell you that Lagrange Point 2 is currently home to the Planck satellite, which is conducting deep space analysis of the remnants of radiation that filled the universe immediately after the Big Bang. And before that, it was home to the WMAP, which is what you're asking about. And WMAP was looking for that subtle temperature difference in the cosmic microwave background, just to kind of get an idea of what was going on out there. And so that was really its job. So this point is not new to spacecraft. It's been home to several in the past, and it's a pretty important place for our spacecraft to be.
It occasionally catches a couple of small meteorites as well, doesn't it? It sort of they fall into it for a bit and then they leave again. And
yeah, things can get stuck in any of the Lagrange points, right? So we say things. Celestial objects can definitely get stuck. Okay. Or I guess I would say hang out on vacation. Take a ride.
So that's pretty cool. I imagine that keeps it in the shade pretty nicely, right? And you're away from the Earth, and the Earth actually kind of glows in heat, and it emits radio radiation as well as other kinds of long radiation. And so you're well away from all of that by sticking the JWST a million miles away into this dimple in space, if you will, called the L2.
Yeah, you're making a great point. Like being that far out, it's very, very cold out there. We'll talk about that in a minute as well.
And that's a big event. Well, that's the next question is, you said infrared, excuse me. So it's an infrared telescope in large part. Tell us what that means in particular.
All right, so I love talking about the electromagnetic spectrum. It's very exciting to be able to talk about that. So what you're looking at on the screen right now is the electromagnetic spectrum, okay? And there are many different wavelengths of light on this thing that we call the electromagnetic spectrum. So people see light in the visible spectrum. So you're thinking people who understand Roy G. Biv from when you were in school, that red, orange, yellow, green, blue, indigo, violet. And there are many other wavelengths out there that we can't see with the human eye. Okay, so gamma rays, as you're seeing on the left, they're at the very, very high end of the spectrum. So we call those very energetic wavelengths. And you can see they're really short. They're really tight together. And
then, they're crammed right up against each other, those wavelengths.
Exactly, yeah, they are crammed exactly like that. Crammed right up against each other like sardines in a can. And then at the other end, you've got the radio wavelengths, which are really long and they're sort of moseying. You know, so you kind of think about that difference. It's the people you meet who have a lot of energy and the people you meet who are really relaxed. And that's the difference. And so infrared, as you see, is sort of right there below the visible spectrum. It's kind of hanging out in the middle. So it's quite a bit longer wavelength than the visible spectrum and definitely a lot more than gamma rays. And so what's really interesting about where things fall in the spectrum is that you can see different things. So we're looking at the same objects, but you actually see different things about those objects.
So if you put an object up on the screen, it would give you some sort of information at the gamma or the X-ray or the ultraviolet. You can see it invisible in most cases, and that's what the Hubble is especially good at in our ground-based observatories. And then you start slipping over into the infrared, and then, that's millimeter and longer, and then finally the laid-back radio, as you were saying.
Exactly.
And so we see that narrow little bit that we call the optical or the visible. That's the Roy G. Biv. And then there's just a universe full of other colors of light, if you will, that are available to be studied, but you need the right kind of sensor to see them. And that's what part of what JWST is going to accomplish for us.
And
is that a correct understanding?
Yeah, you've got a great understanding of what's going on here. So what you're looking at now is you're actually looking at on the right-hand side, you're looking at the visible spectrum of the Helix Nebula. And on the left, you're looking at the infrared. And what's really important about looking at this is that, okay, so you've got certain stars and objects out in space that are emitting these longer wavelengths of light. And those are the ones that the light can actually get through this dust and gas, right? So nebulae are dust and gas. And believe it or not, we think on Earth that this is smoke, like a puff of smoke. And you can just see through it, but it's really thick, it's really dense. And so certain wavelengths of light just can't get through it. But in the infrared, we see those longer wavelengths. And in the radio, we see those. And so that's what JWST is looking for, is that structure. And so these nebulae are places where stars are born. It's a really rich star-forming environment. It's a place where planets are born. And so by looking in the infrared, we're seeing those longer wavelengths and being able to see that activity taking place that we can't see in the visible and at the higher energy wavelengths.
So the visible one on the right is quite colorful. The one that we're looking in infrared on the left is giving us all sorts of views through the dust and gas that are between us and those stars, and they're popping out, whereas you couldn't see them in the visible light. So there's just a huge advantage to being able to see in a little bit different frequency band, the infrared band. All sorts of information pours out to us, and we get to understand what's really going on. I have a mental image of the sun setting when there's been a wildfire and you're looking at it through a lot of smoke, or a volcano has gone off somewhere around the world. You get those beautiful red sunsets. That's partly because it's the white light's being screened by the smoke.
Yeah.
Sort of is, a bit like what you're doing
exactly.
here.
And you made a really good point, by the way. You were talking about those things that you can't see, and you get these really different kinds of amazing images. And so I want to show you this really quickly. So what you're actually looking at here is on the left is the visible image, and on the right is the infrared image. And so you're getting this really beautiful image of this cloud structure and these stars that are shining so brightly that are actually muted in the visible because that light can't shine through that dust. And so we often actually create composites in astronomical research so that you can have that beautiful view of the visible light and all of those colors, plus all of the structure and all of the stars that are out there. So you'll see quite a number of composites out there, usually the Hubble images, and these are Hubble images here. And so you'll see these composited together, which means laid on top of each other, so that you get both the benefit of both types of light.
So the Hubble was modified at some point so it could see a little bit into the infrared. And so that's where we're getting this Hubble image on the right that sort of peeks through the smoke and dust to see the infrared light that's there. I assume that James Webb will do an even much better job at seeing farther into the infrared and more sensitivity than the Hubble has, because it's a
you're 100% right. So
camera.
Hubble can see a little bit into the infrared, but one of the big things you said at the very beginning of the show is that James Webb Space Telescope is going to sort of take over for Hubble. And they're not twins, though, right? So they do slightly different things.
Right.
And so I'm going to show you this really quickly, because what I really want to show you is how far James Webb Space Telescope can see back in time. So what you're looking at here is the star HL Tau, and it's a planetary image, right? So what you're looking at is the star and then the planetary system being born around it. And this is actually not an infrared image, it's a radio image. But James Webb Space Telescope will be capable of helping us to see with more clarity what's going on in these planetary systems that are starting to form. So these black circles that you see in this image are actually the planets starting to form their orbits. Going through the stars.
And they're clearing the dust out of those rings as they go around and accumulate it. We imagine that's what happened in our solar system when our planets were formed.
Yeah, and so it's
similar.
we can't just see our own solar system, so it's helpful to get far outside of Earth so that then we can look at other solar systems. And
this might be a much younger solar system than our own then, because it's still in the formation stage.
Yeah, so this is a really young planetary system that's forming right now. And so it's interesting for us, especially in the infrared, to be able to see these types of things happening. And that's why we use the infrared, is so we can look into those star forming regions and those planetary forming regions, right? So the planet forming regions, excuse me, so that we can see that this is going on and see the birth of planets and see the birth of star systems and see the birth of galaxies happening.
Oh, I can't wait for those images to come to us. That's going to be very exciting time.
It is. It's going to be amazing.
All that information and all that, something we've never been able to do before. Humanity has never seen these things, and now they're coming to us for the very first time and our timeline, and that's just going to be, I just think, absolutely wonderful. Can't wait for it to happen.
Okay.
Okay. So at this point, we're going to take a little bit of a break. If our viewers have any questions, there is an email address at the bottom of the screen. Feel free to send them to us in that fashion, and we'll respond promptly with your answer. And as we take our break, we will switch over to Steve Whitty, who is going to give us the term of the day. Be right back.
Thanks, Don. The term of the month is space telescopes. Space telescopes are above the boiling atmosphere to get sharper images. The telescopes in this image are shown near the part of the light spectrum that they detect. The atmosphere blocks gamma rays, X-rays, ultraviolet, infrared, and microwaves. Getting above the atmosphere is pretty much the only way to detect this light. Ground-based telescopes are often bigger, and bigger gives you better resolution. But radio interferometry from the ground is limited to the diameter of the Earth. Not much you can do except go to space. From 2011 to 2019, the Russians flew Spectre-R, a space radio telescope that extended radio interferometry by a factor of 27. And that's term of the month, space telescopes.
Thank you for the term, Steve. Welcome back to Astronomy for Everyone and our discussion about the impending launch and duties of the James Webb Space Telescope. Amy Oliver remains our expert on staff, if you will, who is helping us to understand things. Before we took the break, we were beginning to talk about the fact that the James Webb Space Telescope can see very far back in time by being able to see the infrared and the radio much better than any telescope that's ever been able to before. Well, can you expand on that a little bit, Amy?
Yeah, great, Tim, great question. So what you're seeing on the screen here now, everyone, is basically how far back the James Webb Space Telescope can see, which is almost all the way back to the Big Bang. So the James Webb Space Telescope is more sensitive than the Hubble Space Telescope and can see longer wavelengths, which means it can see back to when the first galaxies were forming and even a little bit beyond that, so that we get a really good idea of what was going on. And why that's really important is because when we look at the infrared spectrum, and what you're looking at here now is infrared plus visible spectrum. And so that's one of those composites I was talking about. And what we see is that structure, how things are forming, how galaxies are interacting. What you're looking at is actually M51 and NGC 5195. NGC 5195 is the burp at the end of the question mark here. So
oh, I love
imagine
that.
that in your mind. Yeah, that's really what you're looking at. But you get to see that interaction. And so we see more of that in the infrared and with those longer wavelengths. The other really neat thing that the James Webb Space Telescope is going to be able to do is help us see and understand, characterize, and analyze black holes in a whole new way. Yeah, so you probably recognize the image on the screen. You probably are thinking back to April of 2019 when radio telescopes, or the Event Horizon Telescope collaboration, took the first image of a black hole, or created the first image of a black hole. This is a more updated image showing some of that movement of light, okay, orbiting around that black hole. So the James Webb Space Telescope is hopefully going to be able to help us actually see those stars and other objects in that dance and in that orbit around black holes. And how it's going to do that, Tim, I'm going to skip right into telling you about the telescope.
Please.
So It has this giant primary mirror that's roughly 6.5 meters. For those who don't speak in meters, that's about 21.3
Oof, that's
in
huge.
diameter. Yeah, it's a pretty big mirror. I've encountered big mirrors before. I know what 21.3 feet is. This is a really big mirror. So these mirrors are made of this ultra lightweight beryllium, and that's a naturally occurring metal that's pretty regularly used in the aviation industry. And so it's put into alloys with like copper or nickel to make non-sparking tools, electrical contacts, but it's used in the James Webb Space Telescope because it remains stable in shape even in extremely low temperatures. And remember, we're talking 1 million miles away from Earth on the dark side, or the side away from the sun.
In the shade, yeah.
Yeah, and it's a balmy 406 negative Fahrenheit. So
Oh,
that
right.
probably qualifies as pretty chilly.
I would think so.
Yeah, the other thing it has, and probably the more popular feature of the spacecraft, is actually the tennis court sized 5-layer sun shield that attenuates heat from the sun more than 1 million times. And what attenuate means is that it reduces the effect of the sun so that the sun can't heat up the spacecraft. So it helps it to do its job unhindered.
So the sensors stay in a very cold place because they're protected by the sun shield and they're 1 million miles away from the Earth and they're in the shade all the time.
Exactly. And
Okay.
the other last really cool thing I want to show you about this spacecraft is the micro shutters. So you're looking at these very, very tiny micro shutters. And because they're programmable, this telescope can actually observe 100 different objects simultaneously.
Oh my.
Yeah, it's a pretty amazing because that's not been the case in the past. Telescopes generally can look at one object or maybe 2 objects at a time, depending on their instruments and capabilities.
Right.
But the technology is really getting better and better with every year that passes. And the observing capabilities, these increased observing capabilities with JWST are really just the beginning, but it has infrared power to boot. And that's what's really exciting about the telescope and the technology behind it.
So not only does it see in frequencies that haven't really been studied in the detail that we would have liked, but it will be able to look at, say, maybe 100 things at a time because of these programmable micro shutters, if you will.
Yeah. And
That's
I mean,
remarkable,
we're just,
right?
yeah, exactly, right. We just want it to get into space. And so that's coming. So I want to talk a little bit about the launch. So this has been a long time coming. It's been about a decade that NASA scientists and scientists all over the world have been waiting for this. So an Ariane 5 rocket is going to take the James Webb Space Telescope to space, and they're going to launch from the Ariane Space ELA-3 launch complex at the European spaceport near Kourou in French Guiana. And the reason that we launch from places near the equator, Tim, do you know? Do you know the secret? Why do we do that?
I imagine because it throws the object into space with all the force of the planet rotating at the equator. It's like a big heave in the direction. I imagine being in a car and then throwing a baseball as hard as I can or firing a bullet. And that's sort of similar to what launching from the equator does for you. Okay.
Yeah, you're 100% right, Tim. So at the equator, the surface of Earth is moving at 1,670 kilometers per hour, and that is 1,038 miles per hour. That's pretty fast. You would get a speeding ticket for that, but we get to ship those rockets out at that speed, and nobody's gonna stop us.
And I understand they've done 80 in a row successfully from that launch pad with that rocket. So we're feeling pretty good about our odds. We certainly hope so. What else do you have to say about it as we begin to wrap up on the show?
Well, what I was going to say is you're right. We're waiting for good luck. And so the readiness date for launch now is October 31st of 2021. So we're hoping for all treats and no tricks on Halloween this year. And if everything goes as planned and that spacecraft is deemed ready to go, that means it should launch hopefully in November, and if not, by the end of the year. But don't hold me to that, because there are a lot of factors that go into launching a spacecraft like this, and it had to travel to French Guiana in order to get ready for launch. And so there's a lot of things that have to be checked, but I think we're all just really excited for this spacecraft to get out there and to start sending images back, for all of us to start learning more about space and really what's out there.
Again, our guest has been Amy Oliver, and she wears a great many hats for us, and today she was the explainer of the James Webb Space Telescope. We are grateful for your time and your expertise. As we wrap up the show, I want to remind our viewers that questions can be sent to the email address at the bottom of the screen again, and we'd be happy to answer them as fast as they come in. Next, coming up, we will have Steve Whitty once again, and he will be telling us what's up in the night sky. Thank you so much, Amy, and now we go to Steve.
What's up in the night sky for September 2021? On September 22nd, we have the equinox, where days and nights are about the same length. September starts with a new moon on the 6th, first quarter on the 13th, full moon on the 20th, and last quarter on the 28th. We'll start the planets with Venus, Mercury, and Mars, all which set shortly after the sun sets. Venus goes from Virgo to Libra and is best at the end of the month because in the sky it's farther from the sun. Mercury is in Virgo all month. Mars goes from Leo to Virgo over the course of the month. Then we have Uranus, Neptune, Jupiter, Saturn, and Pluto, shown here also on the 1st of September, a few hours after the sun sets. Neptune is in Aquarius and is up all night because opposition is September 14th. Uranus is in Aries and rises a little later in the morning, but is up almost all night. Uranus has opposition coming on November 4th. Jupiter and Saturn are in Capricornus and set a couple of hours before sunrise. Jupiter had opposition on August 19th, and Saturn had opposition on August 2nd. And that's what's up in the night sky for September 2021. Remember, we don't charge for this show, but we may tax your brain.